Right, so let's see if we can explore some problems involving some of the concepts that we've encountered up to this point. So I'm going to start with an unknown spectrum, which is the spectrum you see in front of you. And the first thing I'll note is that we have a molecular formula for this compound. So the signals there must match the molecular formula that we see over there. And the first thing I would require you to do is to note that the integration here and the number of proton signals that give rise to the signals that you see must match the molecular formula. So you can see you've got a ratio of 1:1:1, and that would be a total, if that was read as it stands, would be 2.5 protons, which is not possible in a molecule. So I'm going to try and multiply all of these numbers by 2. And so this by 2 is a single, it's 1, that'll be 2, and that'll be 2, to a total of 5, which matches the molecular formula. So this signal must be the result of 1 proton in the molecular formula. This signal must be the result of 2 protons, and this signal must be the result of 2 protons. So that's the first point. The second point is have a look at the chemical shifts, and this chemical shift may be a bit indeterminate here, but it is interesting to note that these chemical shifts are in the aromatic region. And my first thought when you've got aromatic signals is that it's quite possible I have a benzene ring. I could look for other aromatic systems, but just note we've got no nitrogens, we have an oxygen. So we could have other aromatic systems, but it's a good choice to see whether benzene works, a benzene ring works, and if that doesn't work, then try something else. So first port of call, aromatic system, look for a benzene ring. If that doesn't work, then try something else. Now, if this is in the aromatic region of the spectrum, notice that you have 2 protons that give rise to that signal, and 2 protons that give rise to that signal. But of course, in an aromatic system, you can never have a CH2. That's impossible in an aromatic system because your bond order is too high to allow for a CH2 in the aromatic region of a spectrum. So, if there are 2 protons giving rise to this signal, it means we've got 2 overlapping signals. You have 2 chemically equivalent protons that give rise to that signal. And similarly over here, you're also going to have 2 chemically equivalent CHs giving rise to that signal. So the question is, how do we arrange these 4 protons around an aromatic system so that 2 are identical to each other and another 2 are identical to each other? But the other problem is that each of these 2 splits into a doublet, so each of them must have 1 neighbor, and of course these 2 CHs here must be arranged so that each of them has a single neighbor. And there is one way to do it. You'll see over here, the only way to do it actually is, here's your benzene ring, and you'll notice that this proton is chemically identical to that proton, so those signals will overlap. This proton is identical to that proton, so those signals will overlap. And this proton has 1 neighbor, so it's a doublet, and this proton also has 1 neighbor, so it is also a doublet. So what we see then, and just as once you've drawn that, the only remaining atoms left in the molecular formula are a Cl, an O, and an H, and the only way to connect those into a molecule is to have a Cl group and an OH group. So this is the situation, is you have these 2 are identical. It's got 1 neighbor, it's a doublet, 1 neighbor, it's a doublet, but those 2 are chemically equivalent to each other, and so they will overlap and you will get a doublet. And similarly over here you've got 2 that will overlap and give a doublet. So The chemical that you're looking for in this situation is a parachlorophenol that we see over there. So we have managed to solve the compound from the spectrum and the molecular formula in this case. So let's have a look at another case. So that's an interesting case. We expect to see two signals from this type of substitution on the aromatic system. So we expect to see two aromatic signals, and we do see it, and they're both doublets because there's one neighbor for each. Right, now this is another interesting case. Please note that there is the spectrum was run in chloroform, in deuterated chloroform, and there is some normal chloroform present, and that comes from the solvent. So that signal there is from the solvent, so don't worry about that. Let's have a look at the spectrum and see if we can identify what the compound is. Well, firstly of all, let's have a look at the integration. This integrates to 1, that integrates to 1, 1, 1. I get a total of 5, and that matches my molecular formula. So I know that this is from one proton, that's from another proton, and so on. So we don't have to fiddle around with the integration. All we need to do now is look at the splitting. Now remember, the aromatic region is over here. This is not aromatic, this is aromatic. And we see that we've got 4 protons in the aromatic region. However, we must arrange those protons to give us the appropriate splitting. So for example, have a look at the singlet. That proton must have no neighbors. If it had a neighbor, it would split. This proton must have one neighbor to split into 2. This proton must have one neighbor to split into 2. And this proton must have 2 neighbors in order to split into 3. And there's only one way to do it. And of course, once you've used up a benzene ring with 6 carbons and 4 protons in the aromatic system, you're left with an OH and a Cl as before, and you can attach those to the system to make up the full compound. There's only one way to do it, and this is the way to do it. See, this proton has no proton neighbors, and so you will see that it appears as a singlet. And then let's move our way around. We have got a proton that has one neighbor and another proton that has one neighbor, and both of those are doublets, which you see over there. However, one proton has a neighbor on either side, and if it's got 2 neighbors, therefore it's going to end up being a triplet. So this compound, we have fully assigned the compound. The compound has to be metachlorophenol that we see over there. So the splitting has very clearly defined what the compound is, and we're fully able to define it. And just to mention that OH must appear as this signal that's over here. Right, finally, just please ignore these impurities. This sample is a very old sample from the lab. What I want you to do is I want you to look at the large signals, and we've got a similar compound here. We've got 4 signals in the aromatic region. The integrations 1, 2, 3, 4, 5 matches the molecular formula, so we don't have to fiddle with the integration. So we've got 4 protons in the aromatic region. Notice that 2 of them are triplets and 2 of them are doublets. So 2 of them must have 2 neighbors and 2 of them must have 1 neighbor. And there's only one way to do that, and that's with the orthochlorophenol. You'll see as you go around, if we place the OH and the Cl on the ring like so, this proton has got 1 neighbor, so it'll be a doublet. This one has got 2 neighbors, 1 on each side, so it'll be a triplet. This has 2 neighbors, 1 on either side, so it'll be a triplet, and this is 1 neighbor, so it'll be a doublet. So we expect to see these patterns that we see here, ignoring the impurities that we've got. And of course, we have our OH signal appearing as well on the proton spectrum, because there is a proton attached. Okay, so what we've been able to do in these three cases, we've been able to identify three compounds from their molecular formula and from the splitting in the proton NMR. We have also used the chemical shift. We've identified that around about 7 we have aromatic signals. So we've used the chemical shift, and finally we've used the integration as well. We've used these numbers to make sure we know how many protons are giving rise to each signal. Have a look at this case over here. So what I tend to do in these spectra is I tend to zoom in on a signal. So this signal here is expanded over here. So you can see that this one is a quartet. That's what it looks like close up. And this one here has been expanded as well. It is a triplet. So firstly, I want to have a look at the integration, and you'll notice that there are it's 3 is to 2 is to 5, and the total adds up to 8, which is what we see in the molecular formula, so we don't have to fiddle with the integration. So it's going to be straightforward that we have a methyl group and a CH2 group, but of course around about 7 we can see aromatic signals, and they're a bit of a mess, but you'll notice that it comes to 5. If you choose a benzene ring and you place 5 protons around it, there's only one way to do that. It looks like we have a substituted benzene. So if you have C6H5 and a CH2 and a CH3, the carbons add up perfectly to the molecular formula and the protons add up to the molecular formula. Of course, on the C6H5, on the benzene, it's very difficult to see what the splitting is, and I'm not going to deal with that further. Okay, what's interesting though is why do we get this splitting over here? Why is the methyl group split into 3, and why is the CH2 split into 4? Well, if you have a look at the methyl group, the CH3 is split into 2 because it is neighboring. It has 2 neighbors. It's next to the CH2. And the CH2 is split into 4 because it's next to the CH3. And so we can immediately see that these two signals belong to groups that are attached to each other, that are neighboring. So from the splitting, we know the connectivity in the molecule. We know there's a CH2, a CH3, CH2. We know there's an ethyl group from this triplet quartet that we see. And so this is the compound that we have. It's ethyl benzene. This CH3 must be a triplet because it has 2 neighbors. The CH2 must be a quartet because it's got 3 neighbors. And then of course we have these 5 signals, this integration to 5 from the C6H5, the benzene ring that we have attached. Okay. So again, we have been able to fully identify the compound by looking at the chemical shift, the integration, and the splitting of peaks in this splitting of signals in the spectrum. Right, here's another interesting case. So if you have a look here, we've got C3H8O, and we're going to have to be a little bit careful as we go through. First of all, let's check that the integration matches. Yes, 6 plus 1 plus 1 makes 8. That's perfect. But of course here, you can't have a CH6. That's not possible. So the next bet that you've got to do is that this could be 2 CH3s that are overlapping. So this could be 2 methyl groups that are both doublets that are chemically equivalent to each other, giving rise to a single signal. So if that's the case, we'll have a CH3 and a CH3, which accounts for 2 of the carbons, and then one of these will be a CH, which accounts for the other carbon. Of course, the third thing can't be carbon attached to anything, or else you end up with too many carbons. You've got 2 carbons from a 2 CH3s. You've got a carbon from a CH, So the remaining signal must be an OH. And it's interesting that if you look at chemical shifts, signals around 4 are normally CHs or CH2s or CH3s attached to, that are in close proximity to an oxygen. So this here, because it's integrating to 1, must be a CH that's attached to an oxygen. Look carefully at the splitting. I've expanded it to try and see what splitting there is, and the CH is split into 1, 2, 3, 4, 5, 6, 7. It's a septet, which means that the CH has 6 neighbors. The only way the CH can have 6 neighbors is if it has a methyl group and another methyl group, 2 methyl groups attached to it. So immediately I can see that this is an isopropyl group. This is indicative of an isopropyl group. And does it match? Both of these CHs are doublets because they are next to a CH. So we can identify what we have, and here we have it. The CH splits into 7 because it's next to 2 CH3s. Each of the CHs, each of the methyl groups are next to a CH, so they're both going to be doublets. And of course, OHs, remember, OHs very rarely split. It's very unusual that an OH splits because of fast exchange of the OH. So the OH is never a neighbor to anything, and it never has any neighbors, and so it will appear as a singlet. So again, we have been able to assign all these signals to the molecule and identify what the molecule is simply from the integration, the chemical shift, and the splitting patterns that we see of the signals in the spectrum. So, just to summarize where we've come from in this lecture, splitting of peaks arises from interaction with neighboring spins. We follow the n+1 rule of a neighbor. The size of a splitting is described as a coupling constant, and neighbors will always have the same coupling constant. Where there are 2 sets of neighboring spins, we will investigate complex patterns will arise, but I will deal with that in later lectures, and structures can be determined on the basis of molecular formula, chemical shift, integration, and spin splitting.